Hi guys, my name is Matt Osburn, and I'll be talking about using the deep Q learning algorithm for cart pull control. Okay, so for this project, I want to design a neural network that could control a cart pendulum or a cart pull system to a desired state. It's kind of a very basic dynamic system, and I naively thought, oh yeah, I'll get this up and running in like a couple days, and then I'll throw this at a really hard dynamic system and get it going. But what I found neural networks for control, that's not a trivial problem to overcome. So some quick background here. I won't go too deep into this, but the idea is we've got this cart that's moving on a frictionless track. We've got a pendulum, and we're trying to get this pendulum to hold in an upright position. Okay, and these are the equations of motion for a cart pendulum. It's very simple. You can go look it up in basically any control textbook. But the idea is we really only have control on the force that we put on the cart. Okay, we don't have any kind of torque control to hold this pendulum upright. We can just control how we're pushing on the cart. And oftentimes we call this function U in control systems. Really, it's in this case, it's just our force. And we would like it to be some function of our states. So if we see the pendulum's tipping over, I want to be able to control and adjust that to keep the system stable and upright. So, to recap that, this is the function I like to learn. I like to learn some function of the states that give me the force that will keep this whole system stable and moving where I want it to move. So I started with a really dumb approach. I just randomly sampled the state space and randomly sampled some inputs and tried to come up with a way to score if it'll be better or if it'll be worse or if it's moving towards the origin. And the reason the origin's nice is because I can just kind of arbitrarily move that around and control the system however I want to. And it turns out this is a really bad way to do it. It leads to a lot of local minimum that don't control well. It needs lots of training data. And even then, this just does not work. It really is a dumb, naive approach, and it makes sense to me why we don't do it this way. I then tried out neural ODE for about a week or two, where I was trying to integrate the equations of motion and say I want this function to work out kind of like we did in class. I want to learn the right U function. And this was incredibly slow. And it's also hard because, at least with the package we were using, you need a fixed stopping time before you start training. And that's really bad because the time it takes to converge on the origin changes with your initial condition. So you're kind of comparing apples and oranges with different starting places. How well did this do? How well did this controller do? I have no idea. It doesn't really make much sense in retrospect. And then you get this huge problem of tiny mistakes early on in integration can just lead to huge problems, and then it can go unstable, and it was just also bad. It was just too slow to really iterate on. So then I went to learn Lyapunov functions, and I Googled a ton of papers out there, and I was like, can I use a neural network to guarantee that I'm going to get the right controller? And it turns out, yes, there's a whole body of literature around this. But this would have required me to implement a mixed integer branch and bound solver that was compatible with PyTorch. And right now, at least for the papers I saw, those folks have not really released that into a nice package that you can go download. And you're just kind of on your own. And I said, yeah, I don't know that I have the time to do that, right? And that's when I found Q learning. So after a month of trying everything I could, day after day, trying to get this controller to work, I found a tutorial series on YouTube for reinforcement learning. And that was kind of the game changer for me in this project. And I will freely admit, when I started this on the Q learning, I knew nothing about it. I followed along. I basically verbatim copied the guy's code and said, okay, I'm going to go back and figure this out. So he did it for Flappy Bird. I did it for Flappy Bird, and then I came back and I said, okay, I need to now change the system to do a cart pendulum. And that's when I got into OpenAI Gym, and I figured out how to make my own custom environment, and I feel like it was a really great learning experience. So now that I've gone back and tried to figure out, okay, how does Q learning actually work, I will do my best to explain it to you. So the idea is we would like to be able to predict, given my state and given all my actions, what's the best action? What's the action going to be that maximizes my reward? not just now, but like all the way into the future. And so you can see there's this really kind of intimidating equation. The basic idea of it is it's still kind of like gradient descent. The idea is these Qs are going to be our neural network that's predicting, what's our reward going to be. And then our R is like, what's the reward we're going to get based off of our current state. And then we just kind of have this comparison of like, well, what happens? We have to go back and record a lot of data and say, well, what happened? What are the causes and effects that feed into this equation? And then we end up, it's kind of this wild interplay of these two networks where one network is trying to predict like what is the best possible action I can take to get the best reward right now. And then there's another network that says, well, okay, over all of our experiences, what's the best way to actually maximize our reward based on what we've actually seen, not what we think we're going to see, on what we've actually seen. What has experience taught us? And the idea is we're going to try to rectify these two networks so they're both learning these aspects of like future propagation and also current propagation, and we're going to try to pull them all together. And then in the end, when we're just running it, we actually only use what's called the policy network. So I kind of talked like why two networks. We're kind of trying to learn two things, right? What's the best action right now, and then what are going to be the best actions through time. So we're just trying to minimize the difference between the two. The nice thing about this setup that I really appreciate is it was clearly designed for batching. So there's no neural ODE, there's no custom back propagation that you've got to do. All you have to do is run your simulation and essentially sample as many states and responses and actions as you can, and then mark down like, okay, what's the reward I get? Like how well did I do? And you save them up and save them up and save them up and save them up, and then you can throw it all into the cost function in one fat batch, and that's your update step. And then you go and you do it again. You resample, you rerun it, you see how well did I do, you batch it all together, and you go. And I like that coming from the neural ODE because instead of taking minutes to train with like 100 time steps, I can train millions and millions and millions and millions and millions of integrated time steps on my GPU like instantly. So they call this replay memory. And the idea is you just keep track of like what's my state, what was my action that I took, what was the reward I got, what's my future state now. Right? And then that all interplays into this idea of like, well, how does that propagate down the line? How does that help me get rewards? What's also interesting about this is we have the learning rate for the optimizer, but then we also have, they called it learning rate. I think they also called it a learning rate. I think it's like exploration rate. There's some threshold value where like you just kind of randomly sample and you say at a given time step and you say like, if it was above the threshold, we're just gonna run with what the network says. If it's below the threshold, we're gonna just take a random action. And that's kind of cool because early on in learning, your network's already kind of bad and it doesn't really have a good cause and effect relationship. So early on, you just kind of randomly sample tons of things, and slowly your networks are gonna start to converge on like, good choices. And then over time, over epochs, you reduce this like exploration rate. So in the long run, it becomes very small and you're kind of locked in on your controller, but you're guaranteed good scores. The other thing too that's kind of limiting about DeepQ is that you're limited to discrete actions, which in control theory is kind of a bummer, at least for the cart pendulum, because it'd be nice to be able to really fine tune the forces that we're pushing on the system. And I've read that there are adaptations for DeepQ that do this. I just didn't have time to go learn it or implement it. So that's some future work I'd have to look into. Another huge part of this project was picking the right reward function. So, and all of the things I saw online, because lots of people have done cart pendulum controllers, they really just reward it for every time step that the cart pendulum can stay upright. They give it like a point. And what this does is over time, you get a cart pendulum that's scoring really well and it's staying upright, but the cart itself is just like drifting off into infinity. Like you don't actually get real control like a control theorist would like. I can't just say like, I want you to keep this upright and go to the origin, or start moving to the right, or start moving to the right at a certain velocity. Like, you just don't get fine control like that. So I spent, maybe a week and a half trying to work out, what's the best way, just trial and error. What's the best way to reward this so that it'll stay upright, but it goes where I want it to go? I actually came up on this inverse, this 1 over e to the x cost function. I tried tons of things. I tried negative rewards. I tried, punishments. I tried lots of things. And I found I needed a reward function that kind of always stayed positive. And that might have been my error. That might have been just user error. But I picked this 1 over e equation where we're taking the norm of our state and where we would like to be. And what that does is we always get a positive reward as long as we're upright. And that's good for the optimizer, so it learns to keep it upright. But then we get these spikes. As soon as we get really close to the equilibrium we want to get to, we get these really nice spikes of score. And so it's really nice. I can look and say, well, 1,000 is the theoretical max of my score. In reality, because we're controlling from one spot to another, it's always going to be lower. But through trial and error, I kind of found a score greater than 500 pretty much guarantees you get a really responsive controller that's going to stay stable. And so I was really happy with that. I was glad I came up with that. These are the hyperparameters just for the whole system. So there's learning decay and batch size and memory size. And I made my own custom AI gym environment. And I was really, really proud of that. And syncing up rates between the two networks and just kind of all these different parameters. The network itself is very compact. So even though the project, is probably 1,000, 2,000 lines of code to get this all working and interplaying and saving the memory and graphing and the whole thing, the network itself is very compact. So let's look at some results. So on the left hand, we have a graph of what I called mean rewards. Or the idea is we take 100 different runs, the previous 100 runs, and we look at what was the score, and then we average it, right? So what this will do is this will tell us over time, how well are we doing on our controller, and then the x-axis, I forgot to label it, is the epochs. So it took about 2,000 or 20,000 epochs to train this whole thing, and then on the right you can see this is our exploration decay over epochs. So you can see at about 6,000 epochs is when our controller was exploring at a 5% rate. And I found that was just enough exploration that we could keep making progress, but not too much that our system was unstable. And finally, I want to show you guys, this is the pendulum. So the red dot represents the equilibrium that I'm trying to control to, and the equilibrium can move, and when it moves, the pendulum reacts. This is not a guaranteed stable controller, so there are some times where it'll place a new equilibrium down, and it will crash. It'll go unstable. Like just there, you saw it, reset and restart, and that's because there's no real guarantees on this controller. We just learned it through data, and as long as the equilibrium points are relatively close, it can control to it. But there's no guarantees. So you see how there it was just a big jump, and it completely crashed out. Cool. All right, to conclude, continuous input would have been nice to have. Building a neural net controller is non-trivial, and it's not provably stable. But DeepQ is a really cool algorithm, I think, because it's built towards badging, and I'd like to see lots, what else the reinforcement learning community has, maybe to, help me learn about this further. Okay, thanks.